All right, let's do a little bit of review on vectors for those of you that are feeling a little bit more lost. Just to review, a vector is a quantity that has both magnitude and direction. And the reason we're taking a look at this is as we are doing problems with forces, it is important to know the direction of that force. So an example of a vector quantity is force. It has both magnitude and direction. A scalar quantity has magnitude only. For example, charge, we're dealing with charges and the electrostatic force between them, mass, objects moving, time. Those are simply quantities that have magnitude. It just matters how much they are. There is no direction that goes with them. It doesn't matter up, down, left, right, north, south, but it does matter with a force. So that's the distinction between the two. So if I have a force acting on something and that force is moving to the right, to the left, up and down, how do I account in a problem up, down, right, left, etc.? How do I mathematically work with direction? So the question is, how do we work with vector quantities? How do we work with quantities that have both magnitude and direction? So there are various methods. I call them, divide them into two different ways in which we can mathematically work with vector quantities. And when it comes to addition and subtraction, of course, multiplication and so on is a little bit different. We're going to focus on just adding and subtracting vector quantities. There are two methods. One I call a graphical method, and the second I call a mathematical. All right, so right now we are focusing on what I call a graphical method. And the method that I like to use, there's a couple of different ways out there. One is called a parallelogram method, and it's very similar. I call this method a head-to-tail method. So for this, basically, as we are aware, a vector quantity, right, has magnitude and direction. So if I were to draw a vector, that's an arrow to represent it. The length of that arrow from this end, which we call the tail, and this end we call the head, determines the magnitude. So that's our magnitude. It's a symbol we use to represent a quantity that has magnitude and direction. The angle, I have to find the tail of the vector and imagine a horizontal line drawn from the tail, and I'm going to go counterclockwise until I hit the vector. That I will identify as its direction. So theta gives direction. And again, theta is always measured in a counterclockwise direction. From a line drawn horizontally from the tail. To the right of the tail. Okay. So if I want to represent a vector, let's use force as that example. If I know that there is a force acting on an object at an angle, right? So let's say, just like we showed right there, if this is our force, and actually, let's give it to you in words. So we're going to start with that first. Let's say I had 20 newtons of force at an angle of 55 degrees. So if I want to draw that something to represent that vector, I need to start somewhere. So I put a dot on my paper. I need the horizontal line as a reference point. I need to get my protractor, and I'm going to lay down my protractor. So I'm going to kind of sketch out what would look like a protractor here, right? So we're going to lay down our protractor. And we're going to mark off on that protractor. So that circle should be where your tail is going to be. And we will mark off where 55 degrees is. So I'll mark that on my paper. So then when I go back and I remove my protractor, right? So if we go back and we take away our protractor, this point, when connected with that point, will make a line that has an angle of 55 degrees, okay, to go with it. But I need the length of it to represent 20 newtons. So to do that, I'm going to have to come up with a scale. So let's say I let 1 centimeter equal 5 newtons. Then I need something that is 4 centimeters long, would be 20 newtons. So I'm going to lay down my protractor again, or a ruler. I come along and lay down my ruler, right? And I measure out 4 centimeters. So I'm going to go ahead and do that. And that ends up to be about right here. So that's all the longer that my vector has to be. This vector right now represents a force of 20 newtons at 55 degrees. Let's say we want to add to that a vector that is 30 newtons at 150 degrees. So off to the side, I'm going to think to myself, well, based on the notation of vectors, anything pointing this way would be 0 degrees. Something pointing straight up should be 90 degrees. Something pointing to the left would be 180 degrees. And something pointing down, straight down, would be 270 degrees, based on our notation. So something of 150 degrees should be ending up in this quadrant, right? So it's more than 90, but less than 180. It's more than the 45 degree, right? Because 45 degrees plus the 90 is just the 135. So we should be expecting something around in here, but I can't just estimate. I, again, have to start somewhere. I draw my dot, right? And I imagine my line. I get my protractor back out. And I lay down my protractor and I mark off my 150 degrees. So you can, on your protractor, be careful because you have a 0 degree that starts over here, and you also have a 0 over here that's on the inside. That all depends if you go clockwise or counterclockwise. So make sure you're marking the correct 150. So I put my mark right there. That's the 150 going from this dot right here, even though if you lay down your protractor, there's a dot in the center. So be careful of that as well. I'm going to remove my protractor, right? So I have a nice eraser here. When I connect those 2 points, that's going to give me a line that makes an angle of 150 degrees with this horizontal line as I go counterclockwise. The length of that line has to represent 30 newtons. So again, if 1 centimeter is 5 newtons, and I'm just making up the scale. You get to decide, or it's written on your paper. You have to come up with a scale that will fit on your paper. So if everything is 5 newtons, then I would need this to be 6 centimeters long, is going to be 30 newtons. So again, I will lay down my protractor. You can't see my protractor, but I'm laying it beside my line like this, right? I have a roller. I'm going to lay it right beside it. I'm going to mark off 6 centimeters. And I get that to be right here. So now I will put my arrow. I don't want my arrow to go any longer than that. So there's my 2 vectors, right? So the question was the math side of it. So let's say these are 2 forces acting on the same object at the same time. So the question becomes back to how do I add these? So mathematically, if I say 20 newtons at 55 degrees, and I have to add to it 30 newtons at 150 degrees, what do I get? I can't just add these to get 50 newtons, and then I certainly won't get anything that is 205 degrees. That wouldn't make sense. It would point it down and to the left. So if these 2 forces are acting on the same object at the same time, I need to be able to add them. And the fact that they're pointing in these different directions will affect the final result. So you can imagine, I think we all have enough common sense to say, all right, if one is pushing like that, and another at the same time is pushing in this direction, you probably have an estimate that might be ended up something up in here, correct? But we need an exact answer. And the mathematical method gives us an exact answer. The graphical method allows us to predict. So in order to add these vectors, okay, to add vectors, you can use a method called head to tail. Oops. And basically, it's you keep drawing your vectors together, placing the tail of one onto the head of the previous. Okay, so you place vectors head to tail. Your final answer goes from the tail of the first to the head of the last. So if I use that method on what we have drawn up here, 20 newtons at 55, so I'm going to redraw those down here. Do that real quick. 20 newtons at 55 degrees, using the same scale. So that was 4 centimeters long, right? So there's my first vector. On the tail head of that, I'm going to start my second vector. This one was the 20 newtons at 55 degrees. I measured out my 55. I drew the length to be 20 centimeters, and I'm going to start my next one right here. I have to imagine another reference line. I want to go all the way around to hit the 150 degree mark, which will bring me right over to here. So I keep going around and I draw my line to be a length of 6 centimeters. So I added my second vector of 30 newtons at 150 degrees to the first vector. My answer then goes from the tail of the first vector to the head of the last vector. Oops. So I'm going to connect those 2 points, and that is my answer. So now for my answer, all I want is that result. To get that, I'm going to measure it, its length. So I measure its length to be 6.5 centimeters. And if you remember, we let every centimeter be 5 newtons. So that 6.5 centimeters, 5 newtons for every centimeter. Centimeters cancel. 6.5 times 5 is 32.5. I think, right? 32.5 newtons, but I also need a direction to go with it. So now here's the tail of my new vector. I imagine a new reference line and I go counterclockwise until I hit the vector I'm interested in. I don't worry about these other vectors anymore, and that's my angle for my answer. And for that, I get 110 degrees. That's the mathematical method of adding these two vectors. So if I were to write those in words, I would say when I add 20 newtons at 55 degrees to 30 newtons at 150 degrees, I'm expecting an answer of 32.5 at 110 degrees. Picture-wise, if I have an object, let's say a box of some sort, and somebody's coming along and they're pulling on it with a force like this, and there's another force on it at an angle of the 150 but stronger, the box will move as if there's one force on it acting at the 110 degrees and of a certain value, right? The 32.5. And you would then say that's your answer as if those two forces didn't exist. That is the resultant. These two are called components. This is called the resultant. So for homework or practice, we had this sheet, right? So some of them I gave you already drawn, some in words, just like we explained right here. So the ones that were already drawn, I suggested, so you don't have to like come up with a scale, it's already given to you. You're just going to redraw one vector on the other. I said, go ahead and change this to a plus, right? So I go to my draw. We said, go ahead and change that to the plus, and you're just adding them head to tail. So again, let me just grab one to go ahead and start. So let's look at number 3. I am going to take a look at number 3. And what I want to do is I'm going to redraw this vector onto this one. So what I need to do first is measure the length of this vector, and I measure that to be 0.7 centimeters. And I come down to the vector I want to add it to, taking this one's tail and starting it right here. I measure out a line that's at the exact same angle. So technically we should imagine this line and we go across and we measure that angle and we mark it. And that angle then, I measured exactly the same, line this up so that it is 0.7, the exact same length. So these two should look exactly the same. My answer then goes from the tail of the first vector, right, which is right here, to the head of the last vector. I connect those 2 points, and that's my answer. So I need to measure its length, which I measure to be about 1.3 centimeters. The scale over here, 1 centimeter equals 5 meters per second. So I multiply by the 5 meters per second for every centimeter, and I would get 6.5 meters per second. But I also need an angle. So I recognize here's the tail, right? I choose a different color here. Here's my tail, horizontal line. I have to go all the way around until I hit my vector. Well, the issue is my protractor doesn't measure that big of an angle. It only goes 180. So I need to recognize I already go 180 degrees, but now I need to measure this little angle that is right here. So I have to lay down my protractor. You can't see that, but I'm going to lay down my protractor upside down like this, right? And extend this line, and I'm going to measure off what that angle is. So when I lay that down, I'm measuring off my protractor to be, about 11 degrees. So if this is 11 degrees and I already went 180, my answer should be 180 plus the 11, or 191 degrees. So my final answer for that problem would be 6.5 meters per second at 191 degrees. This one, whoops, done in words as well. Okay, so the solutions to these I'm going to include. You can take a look at those, and hopefully that all helps you make a little more sense out of adding vectors.